This semester I'm adding a new little section to this class that I haven't done in here before, but I'm hoping it'll kind of give you a little more of a bigger perspective kind of on the, mostly on linkages and rigid bodies that we've done in 2D, but also a little bit on, it relates a little bit to rotating coordinate systems. And this is doing rigid body and linkage calculations in 3 dimensions. So far everything, all of those things that we've done, well, yeah, all the rigid body and linkage calculations we've done, all the motion has happened in a plane. So now we're going to talk about what goes into it in 3D. Okay, so 3D rigid bodies and linkages. So here are the main points. The first one is that overall the approach is exactly the same. For each rigid body, you can go through the go through those same 7 steps. You can use the pancake table just the same. So overall, it shouldn't feel that foreign, but there's some new stuff that that does come into it. First of all, the joints are different. Second, the moments of inertia, the mass moment of inertia, are not scalars anymore, they're matrices. The ones we're going to use are just diagonal matrices. So they only have diagonal elements. In general, they're not diagonal. But you can always start with the diagonal matrix and use rotation matrices to come up with the general version. And they're not diagonal, but no matter what, they have to be symmetric. That's not going to come up in this discussion at all, but it's the truth. Anybody know what? No, you don't. So the main benefit of symmetric matrices, the thing that symmetric matrices bring along with them, is that the eigenvalues are real. There's no imaginary eigenvalues. And since these diagonal matrices that we're going to be working with, each element is a moment of inertia, it makes sense that there's a relationship between the fact that the mass moment of inertia matrix is always symmetric and the fact that our diagonal matrices are always going to have real values. Okay, so the first thing I need to talk about is joints in 3D. And there's a couple people who are taking this class in statics at the same time. This is going to be a pretty similar discussion, but in dynamics, it's more than just loads that you have to worry about with joints. You also have to worry about what motions they restrict. So, for example, you have to consider what forces a joint applies from one body to another, but you also have to consider what type of accelerations are allowed for one body relative to the other in the presence of this joint. So I'm going to talk about these joints. I'm going to break it down the same way I did in statics. I'm going to talk about them in order of the number of variables that they provide. And there's a PDF of like a book version of this list. It's not in D2L yet, but I'll put it in after class. And it just gives better pictures of all these, and so you can reference it more easily. But so let's go through the joints in 3 dimensions. Okay, so the first category are joints that provide one variable one load variable and therefore they restrict one type of acceleration. The first one of these is a frictionless contact. So if you have a body like that, that's just supposed to be sort of a 3D view of this slender member in contact with the ground, and that contact, if it's frictionless, free body diagram looks like this. That is a force perpendicular to the surface. And the acceleration that's eliminated is a translational acceleration component perpendicular to the surface relative to, this is the part that's sort of a pain, relative to the base member. Okay, so what does that mean? Well, if this thing that looks like the ground was actually another member that's accelerating, we can't assume that the acceleration perpendicular to that surface is equal to 0. All we really know is that the acceleration perpendicular to the surface of this and that are the same. They can both be accelerating together. Okay. And so this is the issue that makes it real complicated when you go to linkages. It's not too bad when you're just talking about a single member connected to the ground, because the base member is the ground and you don't have to worry about any kind of relative motion, or even worse, when we get to joints that limit rotation, we start dealing with calculating accelerations, angular accelerations relative to another member, which requires the rotational coordinate system calculations. It's a mess. But it's not too bad if you're just dealing with the ground. Okay, the second type in this first category that provides one load variable and restricts one type of acceleration is a roller. So that's just like a ball in contact with the ground. A free body diagram looks like that. So that joint applies a force component perpendicular to the surface again. And the acceleration that's restricted is the same as it was for the frictionless contact. It's a translational acceleration component perpendicular to the surface relative to the base member. One thing about both of these two joints is, notice that in the drawings, if I'm getting these pictures across correctly, there's no way for the ground to pull down on this member. And so that force R can only be in one direction. So R has to be positive in both of these two cases. If you get a negative value of R, the system isn't working like you designed it to work, or there's a calculation problem. Then category 2. This applies 2 load variables. And it restricts 2 components of acceleration. The first one in this category is a roller I think I'll just do this as a single one. So we'll just call this a roller where the idea is that this can only roll along the ground in the direction that it's aiming, you know. And so you could get, if this is the wheel of a shopping cart, you could get behind the cart and push it forward, or in front of the cart and push it backwards. But if you stand on the side of it and try to push it, the direction of the wheel is going to keep it from moving to the side. Okay. Free body diagram. So actually, so the idea here is that this is still in the 3-dimensional view of this. So there's a force perpendicular to the surface, a normal force, and then there's also a force component that's parallel to the surface. Are you following what I'm trying to draw there? actually. That's worse. Okay, anyways, those are perpendicular. So I'll call this N and R perpendicular, R perpendicular to N. So here we have a force component perpendicular to the surface. And a force component parallel to the surface, perpendicular to the direction of motion. This one, can that be positive or negative? And this one, can it be, is that only positive or can that be both? What? Both, yep. So you can't stand to the side of the cart and pull it towards you or push it away. So this can be plus or minus. Then the third category. Oh, I didn't say about the acceleration. So the accelerations that are restricted by the joint are a translational acceleration component perpendicular to the surface, relative to the base member, and a translational acceleration component parallel to the surface, perpendicular to the direction of motion, relative to the base member. Okay, now the third category. So these are, well, there's only one of these. It introduces 3 load variables and restricts 3 acceleration components. This is a ball and socket joint. a free body diagram looks like this. All translational motion is resisted by a force, so you have a full force vector. And the acceleration that's restricted is all translational acceleration relative to the base member. And then, let's see, I guess there are two more I need to do. The fourth category is joints that provide up to 4 load variables. And they restrict up to 4 acceleration components. And there's one of these. It is called a pin without thrust. And you get that if you have 2 members connected by a pin, but there's nothing to keep the members from sliding along the pin relative to each other. That's what the thrust refers to. So it's without thrust because these members can slide along that pin. They can get farther apart or closer together on that pin. A free body diagram looks like this. So there is a force vector this way and this way where these two are perpendicular. Call that R1 and R2. Okay, so that says that these 2 members can't, that pin keeps them from translating in those 2 directions relative to each other. And then also that joint keeps them from rotating about those axes. So those rotations, this couple here keeps this from turning like about its long axis. And this one here keeps that member from swinging around like this. So I'll call that M1 and M2. And so those loads are two force components perpendicular to the pin axis and two couple components perpendicular to the pin axis. One thing that's different about this one is that in some applications, you're not depending on this joint to limit rotations. In those cases, you just don't use those two couples. So there's just no M1 or M2. And the accelerations that are restricted are two translational accelerations perpendicular to the pin relative to the base member, and two, this is the first time we've seen a joint do this, two angular acceleration components perpendicular to the pin relative to the base member. And the same thing is with the forces. Notice that if this joint isn't expected to limit rotations, you can then you'll leave off those two angular accelerations. And then there's one more category. This is 5 variables. Of loads, and it restricts 5 components of acceleration. This one actually, I should say, these are both up to 5 in the same way that the last one was up to 4. you'll have some cases where this kind of joint isn't expected to restrict rotational accelerations. Okay, so this one looks like this. This can be a pin or a hinge with thrust. The thrust means that, you know, the two brackets on the side of this member mean that the member has no ability to translate along the axis of the pin. So that's the difference between the pin without thrust and the pin with thrust. A free body diagram looks like this. So the motion of this member at that point is totally restricted, the translation, so there's a full force vector. And then rotations are still allowed, obviously, about the pin axis, but there's no rotation allowed about either of these two axes. And so that's 1, 2, 3, 4, 5 variables. And so those loads are a full vector of force, and then two couple components perpendicular to the pin. And notice, like pins without thrust, if this joint is not designed to prevent these couples M1 and M2, then you leave those off. If it's not expected to prevent the rotations in the direction of M1 and M2, then you leave off those couples M1 and M2. So if it's not designed to restrict rotations, leave off M1 and M2. And then it restricts five acceleration components. That is 3 translational acceleration components, relative to the base body, and 2 angular acceleration components perpendicular to the pin relative to the base body. And again, if this joint is not designed to restrict rotations, leave out the angular accelerations. Okay, and then, I don't know, maybe there's not too much use in doing this in dynamics, but there is one more category of joints. Let's put it in here. There is a joint that provides 6 load variables and restricts 6 components of acceleration. That's a fixed joint. Yes. Okay, so there's a fixed joint. Connected to a fixed joint, the body can't move at all relative to whatever it's connected to. So a free body diagram you have a full force vector and a full vector of couples. And all accelerations are restricted relative to the base body. That doesn't mean that an object connected to a fixed joint can't move, because if it's connected to a fixed joint with a fixed joint to something that's moving, something that's accelerating, then it's going to accelerate too. So all accelerations, 6 free force components, and 3 couple components. Are restricted, well, relative to the base body. Are restricted. Okay. Any questions jump out at anybody right off the bat about that list? The next thing we have to talk about is how to deal with the mass moment of inertia in 3D. So the mass moment of inertia matrix. Well, in lists of mass moment of inertia for different bodies, they're always given like this. So let's say you're looking at the mass moments of inertia for a slender rod. So they'll draw the rod like this. And then they'll show the coordinate system like this. And then they'll tell you that the acceleration about the center of mass rotating about the x-axis is equal to 1/12 ml squared. And that's also equal to the mass moment of inertia about the z-axis. And then in this case, you treat the mass moment of inertia about the z-axis as basically 0. It depends how thin that rod is. Yes, thank you. And so to write this as a matrix, you just write that the mass moment of inertia about the center of mass is equal to 1/12 ml squared 0, 0, 0, 0, 0, 0, 0, 1/12 ml squared. Where this goes to the x and z diagonals in that matrix, and this goes to the y diagonal in that matrix. Then for a thin disk, if that's x, y, and z, the moment of inertia, all of these are about the center of mass, rotating about the x-axis, is the same as the moment of inertia rotating about, which one is the same as rotating about x? Y, yep, that's good. And then that's equal to mr squared over 4. And the mass moment of inertia rotating about z, so this time, rolling, is equal to mr squared over 2. And so combined, these give you that the mass moment of inertia matrix about the center of mass, class is almost over, we'll make it, is equal to mr squared over 4, 0, 0, 0 mr squared over 4, 0, and then 0, 0, mr squared over 2. And then the last one is a thin rectangular plate. X, Y, Z, and we'll say that that distance is L, and this distance is W. Then the mass moment of inertia about the center of mass rotated about x is equal to 1/12 ml squared. The mass moment of inertia rotated about y is 1/2 mw squared. And the mass moment of inertia rotated about z is 1/12 mass times the quantity L squared plus W squared. And all these together give you that the mass moment of inertia matrix is equal to 1/12 ml squared 0, 0. Then 0, 1/12 mw squared 0. And then 0, 0, 1/12 m quantity L squared plus W squared. Okay, and this is the last thing I'm going to say before my computer closes. Notice you just use the parallel axis theorem just like you did before, element by element. So you use the parallel axis theorem like in 2D, element by element. Better save this stuff. Okay, so we'll do a couple example problems on Wednesday, and you'll see how it all fits together.